again. I am Greg Swayzer. I'm with the University of Minnesota's Regional Sustainable Development Partnerships. We are a program at the University of Minnesota Extension. What we do is we connect innovators who are farmers or community groups or just individuals in the communities. We connect those groups with the University of Minnesota and the university's resources. So we help people working on sustainable development ideas that are homegrown, homespun around the areas of clean energy, natural resources, sustainable communities and tourism, and sustainable agriculture. So over the past few years, we've been working on this Deep Winter Greenhouse Initiative, which started about 10 or 15 years ago now with Carol Ford and Chuck Wabel when they built their first greenhouse, which you see in the upper left corner here. They built their first deep winter passive solar greenhouse and published the Northlands Winter Greenhouse Manual with help from the regional partnerships. And they connected with us to help spread the word and do workshops and develop this Deep Winter Producers Association. From there, this work has spun off and we've ended up developing deep winter greenhouse, publicly available deep winter greenhouse blueprints with advanced versions of this concept. And we continue to work on it now with a new, larger farm scale deep winter greenhouse. And we've done horticultural research and all sorts of workshops and outreach. So this work just keeps continuing to go on. And it's been great. And we also do this around all sorts of other issues, food related, clean energy related, natural resources and other. And today we'll be featuring Dan Handeen. Dan Handeen is a research fellow at the Center for Sustainable Building Research with expertise in passive solar design, net zero and high performance residential construction, building science, community design assistance, exhibit design, and materials life cycle analysis. He holds a Master of Architecture from the University of Minnesota and a permaculture design certificate and teaches in the architectural program at the U of M. Handeen has been working with the regional partnerships over the past several years to design the Deep Winter Greenhouse 2.0 version and has helped farmers and contractors build these according to the specs. Recently, Handeen has been developing the designs for the new farm scale Deep Winter Greenhouse with size and cost appropriate, which is size and cost appropriate for small and mid-scale growers.
Hi, thanks everybody. Thanks for joining us on a beautiful, well, here in Western Minnesota, coming to you live from Sparta Township, about 170 miles straight west of the Twin Cities. Just a little heads up, I did have some internet issues earlier today. I don't anticipate that'll happen again, but if for some reason I do go blank, just hold tight. I should be back up and running in 10 to 15 minutes, okay? That said, really looking forward to this. We had one of these, the design-related winter greenhouse webinars on Wednesday. Went really well. Lots of questions came in, and I'm looking forward to doing it again with all of you. I just noticed that there are some people that have come back for this one. A lot of the content will be repeated from Wednesday, except I will try and dig into the 3.0 design a little bit more deeply. And but I'll follow a similar format, which is I'm going to first go through some slides. We'll talk about the principles that underlie winter greenhouse design, and we'll review what we call the 2.0, the Deep Winter Greenhouse V 2.0. And that's just a good way to talk about the principles, and those are the ones that we've built and have had some success with. So we'll go over that first, and then we've got a little video tour of one of the 2.0 greenhouses, and then I'll dig into the farm scale winter greenhouse plans. And I will try and take little periodic breaks as we move along to try and hit some of the questions. Again, as Greg mentioned, please put your questions up in the Q&A field. Let's see. That's what I'll be keeping an eye on for Q&A. We also have Carol Ford, who has joined us today. Say hi, Carol. She is the production guru. So if there are questions that relate to what you do in the greenhouse, she will she'll be able to address that stuff. So again, the focus of this particular webinar is about the design of the greenhouse, and particularly the 2.0 and the farm scale winter greenhouses. So without further ado, let me share my screen. All right. So, are you seeing my presentation or my presenter mode, Greg?
I see your presenter mode.
Okay.
There you go.
How's that?
That is great.
All right. So I've taken the liberty of renaming this webinar a little bit, in that I really want to cover a lot of the principles. I know a lot of you are joining us because you have more general questions about designing your own winter greenhouse. And I know that there are many, many different ways to approach winter growing. And so I really want to try and set you guys up for success in whatever particular type of route you choose to take as you try and grow stuff in the winter. So I do want to acknowledge our supporters through this, especially the regional partnerships, SARE and the Minnesota Department of Agriculture. This has been just a wonderful cohort, grouping of people that have come together to work on this project, and we're seeing the successes over and over. Just great people to work with. I do want to reiterate also, this is the website that Greg referred to earlier, that he gave you the short version. This will also get you there. We've also posted it up in the Q&A. So if you click on the answered questions in the Q&A tab, you will find a direct link up there. So feel free to peruse that as we are talking away here, but that's where you'll find all of this information. That's where the plan sets are, our enterprise reports are. That's where pretty much everything. That's, as Greg said, that's the clearinghouse for all of the U of M's winter greenhouse related stuff. So I wanted to talk about deep winter greenhouse design first, generally. I also, before we get into this, I just want to be perfectly clear that we're not saying that this is the only way you can grow in the wintertime. And I look at the deep winter greenhouse as we define it at the U of M as sitting along a whole spectrum of what we call, oh, somebody's seeing the presenter screen. Thank you. Greg, what are you seeing?
Yeah, sorry, it is the presenter screen. See your slide
go.
to the left in the next one.
Okay, thank you. How about that? All right, thank you, William, for that clarification. I want to be clear that this is it's a spectrum of what we call CEA, or controlled environment agriculture, right? We're manipulating the environment somehow so that we can have or create conditions conducive to growing what we're trying to grow. So that could be everything from low tunnels, right? Just remay row cover over something that's grown in the ground to, maybe a cold frame, high tunnels, winter greenhouses, deep winter greenhouses somewhere in here, and then all the way to something like vertical farms where it's completely, hydroponic and artificially lit, that sort of thing, right? So all of these things are on a big spectrum, right? And so we see this fitting in somewhere. I like to also say that you can grow anything pretty much anywhere if you throw enough energy at it, right? And really our goal with the deep winter greenhouse work is to give precedent to passive solar design. So we're trying to get as much or capture as much of the sun's energy as we can and use that as our primary heat source, right? And then, as we'll see, you obviously have to have some backup, supplemental heating, also known as insurance. But we're taking basic passive solar design principles and utilizing that as far as we can to meet our primary energy loads, right? So a couple of the things that we look at as far as how we define a winter greenhouse, and one is that we're optimizing for winter production. This isn't designed as a year-round structure. There are modifications that you could do to, kind of extend the seasons, shoulder seasons, that sort of thing. But we're really trying to, especially with the deep winter greenhouse, the 2.0 design, we're trying to really target this niche of, say, late October to, March, April, somewhere in there, where we're really in the depths of winter, right? So there's a number of very specific design responses that we do to, design for that goal, right? You would change things if you wanted to try and make it usable year-round or something like that. So I want to be clear about our targeted goals. The second is that we're utilizing a thermal mass for heat storage. And there's many approaches to thermal storage. There's phase change materials, which we can talk about later. And there's different approaches to thermal mass. And so many of you are probably familiar with the SHCS, or the Subterranean Heating and Cooling System, a term popularized by John Cruikshank, an early passive solar greenhouse advocate and designer, now deceased, unfortunately. Just a wealth of knowledge. And then you're probably also familiar with the GATT system. Series Greenhouses out of Boulder, Colorado refers to it as geo-air heat transfer, right? And so the principle here is that we're utilizing some kind of thermal mass, whether it's soil or rocks, as some way to retain heat so that it can be utilized again later, particularly when the sun is not shining or at night. So on we go. So looking at the V 2.0 design, and so we like to say that the V1 was Carol and Chuck's greenhouse. Carol, who's on the call with us here, and so I was contacted by the regional partnerships to basically come up with a set of best principles and talk to designers, operators, consultants, and was really fortunate enough to travel really around the country and talk to people who are doing this type of work, and come up with what we call the V 2.0 design. And so as we were putting this together, a set of questions came up. How do we respond to these? One was, how do we optimize our solar heat gain? So that is, how do we get as much of that sun's energy inside the building as possible during the wintertime? How do we retain that heat once it gets into the building, right? So that we're not losing it. It's one thing to capture it, but then it's another thing for it to leave right away. And then lastly, how to improve construction details. One very, I'd say, consistent theme with the greenhouses that I visited was that, the design was well thought out, and theoretically it would work very well, but there was details, particularly in corners or where different types of materials that would meet, that somehow there wasn't a fully anticipated way of how that was going to go together. And that became a draft or a leak or some kind of failure that ultimately really starts to harm the function of the greenhouse, which is keeping that heat in, right? So a couple of the defining features of the 2.0 design. One is the glazing angle, and this here on this side, this is a section profile of the 2.0 design, and basically this portion here, this is the growing area. This portion up here, we call this the packing shed. I look at it as an airlock. We'll talk about that in just a second. But this is the glazing wall right here. This is angled at 60 degrees off of horizontal. And the reason it's at 60 degrees is because it corresponds nicely to not just the winter solstice when the sun is actually lowest in the sky, but also to January 21st, which in Minnesota is historically the coldest time of the year. So we're designing not only for the shortest photo period, but also when we're really trying to capture the sun's rays. We're trying to make this as perpendicular as possible because we get the best solar heat gain transfer, right? I did see there was one question that had come up in the registration about modern glazing and that it allows light through. Yes, modern glazing, especially the frosted ones or diffuse ones, they do a great job of letting the light portion of the spectrum in. But along with the light portion, we also are trying to get the heat portion of the sun's electromagnetic radiation to come into this building, right? So we're trying to make this as perpendicular to the sun's rays as possible during the winter time. The other reason this is 60 degrees is because it's relatively easy for a builder to figure out, right? It's not a 45, that would be probably the easiest thing, but 30 degrees, 60 degrees, 90 degrees, you know, should be pretty understandable by most builders. It's not some weird, like, you know, 56.4 degrees or something like that, right? Pretty standard. Second defining feature was really about the air control aspects. So this is manifested in two different ways in the 2.0 design. One is that we're trying to control the mass of air that we're containing in the growing area, particularly because we've worked really hard. We built this crazy structure to try and get all the heat in there. We want to make sure that it stays inside. We're minimizing any drafts and really trying to be careful about humidity control, actually. So one of the ways that we do that is by, sorry about that, is by putting this, the packing shed area, as we call it, on the northern side of the greenhouse. Again, this is our growing area. This is a plan of the greenhouse. And so we've got doors to the exterior here. This is the only door that actually leads directly into the growing area. And so this is acting as an airlock or a lobby, if you will, right? So that we don't have actual airflow that's going directly in and out of the greenhouse, just when we're walking in and out. This also becomes a nice area that has some conditioning. You know, it's not outdoor conditions, so it's a great place to store things like soil mix or fertilizer or whatever you're working with in the greenhouse that isn't actually taking up space in the growing area, right? We really want to try and maximize our utility of this area because, frankly, it's relatively small. And secondarily, we've put a lot of work into it, right? To make this a very particular growing environment. And so we want to be able to utilize it as much as possible. Take a quick look at the questions. How does the angle of glazing relate to latitude? Very good question. So obviously, the sun is going to be at different heights in the sky depending on your latitude, right? You can look at, I mean, there's all kinds of websites and apps actually that can tell you the sun's angle throughout the year for your particular latitude. So very easy to Google. But you also kind of want to think about it as a balance between what your design goals are. Again, if you're trying to go for the middle of the winter time. Also, if you're in a more temperate area, maybe say you're down in Missouri where you don't actually have that long or that cold or extreme of a winter, you know, you could make certain other sacrifices that might not be optimizing for solar gain during the coldest night of the year, right? So again, it depends on your goals. I will say just generally, no matter where you're thinking of building your greenhouse, you want to do some type of solar site assessment. So that is taking stock of what the obstructions are to the sun's path as it moves across the sky. Taking into account that that angle, that sun's angle, is going to change pretty severely, of course, depending on your latitude, over the course of the year. So you want to make sure that you're getting sun when we really need it, right? During the coldest months of the year. So in Minnesota, we need a pretty wide open exposure to the south. And probably secondarily, more importantly to that, is exposure to the east, because that's when we want, you know, early morning heating, really. So looking further, the enclosure, again, the ways that we're trying to keep the heat in once we've got it into our greenhouse here. We've got R23 rock wool insulation or mineral wool insulation. They're synonymous. This is exceeding Minnesota residential code amounts. We've got about R30 in the roof. You'll also notice here that we've got continuous insulation around, sorry, I have a very sensitive mouse, that we've got exterior insulation on the outside of our stem wall, right, our foundation wall. So we have insulated both below grade and above grade, okay? We also have vapor control. This is very similar to the vapor barrier in typical residential construction, trying to make sure that we don't get hot, humid air from inside the greenhouse migrating into the wall cavity and then meeting a dew point somewhere in the cavity and condensing out, right? We want to be very careful about where we are keeping our vapor. We expect, this is a hot, humid environment. This is a growing environment. We know there's going to be moisture. We know there's going to be humidity. And because it's, you know, there's pretty wide fluctuations in the temperature, it's going to get hot. So that that humidity is going to be mobilized. We expect that it's going to happen. We just want to be careful about where it happens. And so we want to make sure that it's not having the chance to move into the wall. Other places like here, this is the south glazing wall. And we expect, of course, there is going to be condensation hitting this wall. And then we've got this angled sill here. So any water that condenses on the backside of this glazing wall can then run down this and then drip off safely into the inside. It's not going to sit on the sill and rot its way into the ends of the rafters or into the sill itself, right? So doing careful detailing to anticipate where we're going to see humidity or vapor problems, right? Or water. Then lastly, and probably the most distinctive or defining characteristic of the U of M greenhouses is our approach to the thermal mass. And this is a variation of systems that you've probably seen, except what we've done is that we have a larger particle rock, about 1.5 inches to 1.75 to 2 inch pebble size, right, or particle size, that fills up this area. This gray box indicates basically a big mass of rocks. Then we have 2 horizontal plena that are buried on either end of that, right? The spaces in between the rock actually allow the air to move through. So the principle here is that here's our glazing wall on the south side. The sun's energy comes in. It heats up air inside. That hot air rises to the peak of the greenhouse and gets drawn in the ends of this duct. It gets drawn down through this vertical duct and then is distributed through this plenum, which has, it's perforated essentially. Then the air is drawn out of the plenum through the spaces in the rock bed, right? So the hot air is moving directly across the surface of the rocks. On the other end here, on the south end, we've got the exhaust duct. Essentially, this is also a perforated duct that's sucking the air basically through the spaces in the rock bed and then up and out. It's all drawn through. This is a inline, essentially an 8-inch radon fan that is sucking all of that through. That's what's actually drawing the hot air in from the top here. And then it gets redistributed back into the growing area through another horizontal distribution tube right here. A couple things to note about this is that it's important that we have the top of this sealed. So we essentially have an intake into this essentially big packed duct, right? We have created a big box full of rocks, but it's sealed so that we only have one intake and one exhaust. We don't want a bunch of leaks around the corners or anything, because that's going to limit the effectiveness of our fan, first of all, and also then, of course, limit the effectiveness of our rock bed thermal mass, okay? Let me take a look at some questions here. I'll answer the insulation question quickly. Fiberglass saturates much more easily compared to rock wool. Rock wool will retain its R value. It can get wet as long as it can dry out. Its performance isn't affected at all. Really, the crucial thing here is the vapor barrier. I'm responding to Tim Clymer's question here about mineral wool providing a media to grow fungus. Fungus needs heat, water, and food. And if we can take out that moisture component, that is the thing that we're trying to control. And so it's really important to detail the vapor barrier in the greenhouse very well. Make sure that it's sealed. Any places where you might, where it's in front of a wall cavity, and taped any seams that you have in the continuousness of that vapor barrier on the inside. I will say in the farm scale winter greenhouse design, we've changed the design of the wall section so that we don't actually have any cavity insulation, and the vapor barrier then is not a concern. Window angle is a normal window that is just 60 degrees more angled. The windowsill is also angled to exaggerate the angle for dripping. Yeah, I would call that a sill plate at the base. It's not, it's a normal one, but it's just 60 degrees more. I guess I'm not fully understanding your question, Catherine. But yes, we're trying to encourage drainage as much as possible. if the glazing wall is at 60 degrees, that sill down here, that, you know, the component at the bottom, that's angled at essentially 30 degrees, so that it's a 90-degree angle between those two, between the rafters and the sill. Relative performance of insulation exterior versus interior of the stem wall. Great question. So that is going back to this little detail right here. Now, you figure you're doing a stem wall. Really, I mean, the most important thing is that we're trying to get continuousness of the insulation as we can, right? The reason that we've put the insulation on the outside of our stem wall is because we want to be able to use this concrete as additional thermal mass, right? We can put it on the inside and we could fill it up with a rock bed and that would still be effective, but then only our rock bed would be our thermal mass, right? This way we also get to use that concrete that's already on the inside of our thermal envelope, on the inside of the insulation, as part of our thermal stabilization, right? We get to use it as thermal mass, so that's why we have it on the exterior. Why not closed cell spray foam that acts as a vapor barrier? Go for it. The reason that we've specified mineral wool and cavity is because of environmental impact. Polyurethane spray foam has pretty high global warming potential, depending on the blowing agents that are used. So really from an environmental perspective, we opted to go with mineral wool insulation for this particular design. But you know, if you have no qualms about it and you can afford it, it's also, you know, usually got a pretty decent price point. You know, but there's no reason why it couldn't be used. It's great. How do you keep dirt, etc., from filling the spaces between the rocks below the greenhouse? Good question. Essentially, you have a layer of landscape fabric that goes over the top of the rock bed, and then some kind of compacted layer on top of that, right? So it's preventing any migration of fines down that would otherwise clog up the matrix in between the particles. Has anyone used ICFs or insulated concrete forms for the foundation wall? Yes, you see this fairly frequently. ICFs are great. However, what that does is then it basically sandwiches your potential thermal mass in between two insulated layers. So it speeds construction and it does provide insulation, but I really wanted to try and be able to incorporate, again, that concrete block thermal mass to the interior of the building, right? So, you know, one approach would be to like try and use ICS and then strip away the interior layer of styrofoam, but most people aren't going to do that. So yeah, you can use it. I just think, you know, from a design perspective, from the utility of that actual thermal mass, you know, it's not as ideal. Why'd you choose a rock bed over what I've seen in other designs? Because, okay, this is a good question. Why did we choose a rock bed over basically putting 4-inch perforated pipe through soil or something like that? Well, the main reason is that those systems, and as you'll see in one of the systems for the farm scale greenhouse, is it has what you call transit ducting, and you've got a plenum here, or a manifold rather, manifolds on either end, and then you've got smaller ducts that connect those two, right? And so what it's doing is that hot air comes in one, it travels through the ducts, and then exits out of the other manifold, right? There's not really a whole lot of incentive for the heat to transfer out through the wall of the ducts into the surrounding thermal mass, right? Yes, it will, you know, but it's ABS plastic, typically not a great conductor to begin with. So there's not a whole lot of incentive, if you will, for the heat to migrate into your thermal mass. With the rock bed, we're actually pushing the air or sending the air directly across the surface of the rocks, right? So it's in direct contact with the rocks. So it's got incentive to you know, basically make contact and transfer the heat directly. And we have huge interaction, basically, right? Because we have so much surface area of all those individual particles, and the air is moving broadly through that. It's, you know, it's just there's no comparison with the amount of volume or surface area that's in contact. How are you sealing the rock bed from the greenhouse? A couple different approaches. Some places have used a piece of landscape fabric and then compacted soil over the top, usually a class 5 or something like that, something with fines in it that you can really compact down. Or other places have actually poured a concrete slab with a gasket around the outside against the stem wall. Here's a quick question. Pouring a cement stem wall, any models for shaping that angled part of the top that receives the sill? I would say just wait till it's setting up and then use a jig or something so that you're screeding it at 30 degrees. Or you could build your own form if it's too liquid. Okay, I'm going to continue on with the presentation here. Let's talk about this. I'm going to turn it over to Greg quickly because he's going to share the video. So this is a little tour. Like I said on Wednesday, ideally I would have, been able to have my cell phone in one of the greenhouses to be able to show you, inside of one and all of the different aspects of it. But of course, because of COVID, we're not able to do that. And so we've got basically a virtual tour, right? So there will be some redundancy in this to what I've just spoken about, but it will get you inside so you can actually see a little better what it looks like inside the V2.0 greenhouses. So I will stop sharing. Okay, you got it, cool. Greg, I'm not hearing anything. I think it may actually listen to the speaker from your computer.
Yep, I forgot to hit the buttons there. Let me try again. All right, how's this?
Handeen. I'm up at the Deep Winter Greenhouse at the Bemidji Community Food Shelf in Bemidji, Minnesota. This is one of the 5 following the prototype design, the DWG V2.0 design that was built through the Extension Service, the Renewable Sustainable Development Partnerships of the University of Minnesota. And I'm going to do a quick walkthrough. Some of the things you can see in this view right here are the steeply angled glazing wall. This is at 60 degrees, corresponds to the coldest night of the year here, or the coldest day of the year rather, here in northern Minnesota. Also the ventilation window, as you can see up here, and then yeah, that's basically it. This is a triple glazed polycarbonate glazing. It's about R2.6. The rest of the walls are insulated 2x6 frame construction with mineral wool insulation. There's R21 in the walls and R30 in the roof. I'll go inside and we can check some other things out. Going into the what we call the packing shed area right now. This is a little area on the north end of the greenhouse. It's 8 feet wide by 24 feet long. That's the entire length of the greenhouse. This essentially does 2 things. One, it gives storage space for growing media and that sort of thing. You can see some of the peat and fertilizer, other stuff that they're storing in here. It also secondarily acts as an airlock so that the windows to the exterior are here, and then the window to the actual, or the door to the actual growing area is right here. And so we'll go into that right now. We are inside. This particular greenhouse, let's see, a couple different design variations. One is that they used a metal corrugated siding material for the interior finish. That's fine. They also did a nice job of doing vapor sealing on the interior for this cavity stud wall construction. Again, the basic principle by which this works is that there is solar gain that comes in through the glazing wall. The hot air rises to the surface of the greenhouse. You can see this duct up that goes along the interior of the peak of the greenhouse. That is open on both ends. You can kind of see up there. The hot air is drawn in through that horizontal duct back here and then down below into the rock bed, which is underneath us. In this case, we've got a cement floor, basically that is capping the rock bed. It's about 4 feet of 1.5-inch diameter river rock. This basically explains what's happening down there. We've got this little schematic. Essentially the hot air goes in here, comes down here, and then it's distributed in a horizontal plenum. This is perforated, and then it makes its way. The hot air makes its way through this 4 foot thick rock bed. That air then exits the rock bed. Basically, a sealed duct comes out here at the base of the glazing wall. It's all drawn through. It's sucked through from up there, from the ducts all the way down through the rock bed by this single fan. This is an inline, essentially a 8-inch radon fan. And then it's exhausted out into this horizontal plenum at the base of the glazing wall. And basically just recirculating the air through the growing area and then down again through the rock bed. The fan is controlled by a couple of thermostats. Ideally, we've got one set for the cold temperatures, essentially the times when it would be extracting hot air or heat from the rock bed and reintroducing it into the growing area. And that would be set for, I don't know, maybe 40 degrees, something like that. And then the other end is when you'd be charging up the rock bed, and so setting that to something like maybe 65 or 70 degrees. So that's when you have the fan on to suck the hot air out of the growing area, and you're injecting that heat into the rock bed underneath. There's ventilation windows on both ends. These are currently just manually operated right now, crank out casement type. They're regular vinyl frame double pane windows. Basically the reason those were chosen was for tight air sealing. We're trying to basically control any drafts that would be happening in here. Having a little bit of issue with freezing during the really cold times and when we've got excess moisture in the air. But still working on how to address that issue. We've got our backup heater here. This is essentially a 2-stage electric resistance garage heater, more or less. And this is our backup heating. Again, this is our insurance. It only takes one time to freeze everything out. So in case that should happen during, after a couple really cloudy days or something like that, really cold snap, then that can provide backup heating. What else? Temperature in here currently is, I don't know if you can see, it's about 82 degrees on the surface of the metal intake duct, and it's about 82 degrees in the regular growing area too. It's about 65 degrees outside right now up here in Bemidji, but nice sunny day. We've got the ventilation windows open too, so that might be affecting the temperature a little bit. As far as what's growing in here right now, they've got some starts and some greens going. They're working on different configurations of planter setups. And so they're just getting into really how to utilize this space. They had some personnel turnover this past winter, so they actually weren't in optimizing the operation just because they didn't have enough people to run it. So we'll see what happens this coming winter. Also, with this particular greenhouse, we've got a monitoring system set up, partnering with the U of M's Solar Energy Lab through the Mechanical Engineering Department. We have set up an array of thermocouples. Basically, it's measuring the temperature within the rock bed. And this consists of 45 different thermocouples that are arrayed, again, within the rock bed. We've got, actually I've got a little photo right here. I don't know if that's visible, but this shows basically the filling of the rock bed. Here we've got the horizontal plana, and then there's 9 columns in here, 9 stakes, and those each have 5 different thermocouples mounted onto them. All of the wires from the thermocouples come up here through a tube at the back of the greenhouse, and then that is all attached to a data acquisition computer, and that when it's in operation should be logging the temperatures throughout the rock bed at I think it's a 5-minute interval. Also, we're measuring the temperature in the intake of the duct, and we're measuring airflow through the duct, so we know exactly how much air is moving through the system. We are still waiting on definitive results from that, unfortunately. So please stay tuned for more results on really what the temperature profile looks like within the rock bed, and then that will lead us to some other ideas about how to optimize the size and configuration of the rock bed itself. So I think that's it. One thing that was mentioned on the Facebook page was that this greenhouse was in stealth mode, and that was because they actually had some glare issues. The sunlight was bouncing off of the glazing wall and disturbing some of the neighbors down to the south. And so they had a shade cloth installed over the exterior surface of the glazing for a while. That's what those the wooden strips are on the exterior of the glazing there, and they have since put up another fence to the south, and I think you can see that that actually blocks any reflective glare that would go out and disturb the neighbors. So so that's what that was for. Other than that, I think I've just about covered everything. This is really one of the I think the tightest greenhouses we have. We don't have any blower door results or anything like that yet, but really proud of this structure. They've done an outstanding job of both the construction and finishing everything out. So any questions, again, as always, please feel free to either write on the Facebook group or contact me directly via email. All right, thanks, good luck.
Right. Thanks, Greg. Right. We still good there? Full screen? Give me a thumbs up, Greg, or thank you. Okay. So we've built 5 of these around the state, 1 in each of the 5 regional partnership regions. And so this was the first one that was built. This is up near Finland, Minnesota, built in partnership with the Organic Consumers Association. This, boy, when was that built, Greg? 2015 or 2016? This is the grandpappy of them all.
I think it is 2016.
Yeah, that sounds right. Yeah. And this one is the one that we just toured on the video at the Bemidji Community Food Shelf. This one is down near Madelia, Minnesota, south of New Ulm, Mankato kind of area. This one is in Pillager, Minnesota, near Brainerd. And, pardon me. And this one is near Lake City in southeastern Minnesota. As mentioned in the video, we've set instrumentation up in a couple of these greenhouses. In this one down at Lake City, we have over 250 thermocouples arrayed through the rock bed. So, and we're still awaiting results. Y'all, I really had hoped to be able to provide some during this webinar. We actively have a mechanical engineering Fulbright student deciphering the insane numbers of data points that have come out of this thermal mass. But hopefully we'll have some legitimate detailed 3D temperature profiles. We'll be able to see really how deep the temperatures are penetrating down into the thermal mass, whether we need to shrink it or make it larger, or if there's any eddies of air within the thermal mass. It should start to give us a good picture of what's actually happening down there. We also have instrumentation in this one, the Bemidji one, and the Pillager one. We've got, again, 45 different thermocouples in each of those to help verify. Those are kind of a backup. So this is just a quick shot of what's happening in there. There's this one, for example, they used a compacted fill over landscape fabric over their rock bed thermal mass. And so they're planting in raised beds. They also put in sleepers over that compacted fill, and then they put wood planks down over that. So they've actually got a wood floor in their greenhouse. But they are planting in raised beds, so they've got some stuff that's growing a little bit longer here. You can see there's chard and there's some, I don't know, this looks like garlic or onions. And then other than that, a lot of what people are growing are more kind of quick churn, fast cycled salad greens. And Carol can talk at length about all this, that we've done some horticultural research in partnership with the horticulture department here at the U, looking at what specific varieties do best in this type of environment, and also testing growing media. And we're also doing some testing of optimizing light within the greenhouse in these short days, right? So a quick glance into how it's working. I mean, really, we haven't been able to get a good sense of how much energy the thermal bed has been able to store, but we are able to see how much backup energy we've needed. And so I put this stuff up. We did electrical monitoring at 2 locations with some decent results. And this one is for the one near Madelia, Minnesota. November, almost 500 kilowatt hours. December, 430. January, we lost the data signal for a while. Again, rural internet connections can be kind of tricky. February, 423 kilowatt hours. It's roughly about 10 cents per kilowatt hour. And so, you know, if you calculate that out, that means it was about $43 in backup heat for the month of December in Madelia. And I also want to be clear that these numbers also, therefore, the total electrical consumption, not just the heating portion of the electrical consumption. We have put electrical backup heat in these V2.0 prototypes for a number of reasons. And one of them is they're relatively easy to track. But these numbers here that we've shown, they are for everything. So that's all of the other circulation fans, any lights, any, you know, chargers or whatever. I think, yeah, I mean, some places have, like, you know, refrigerators. I think Madelia might have been running a dehumidifier occasionally in here, but so it's still pretty modest supplementary heating expense. When they switched over toward the end of the season, they were still using the greenhouse to do starts. I think, Carol, correct me if I'm wrong, but I think they were starting their transplants in there. But that dropped down to about $23 a month. Still pretty high energy consumption. That kind of surprised me, but I think that's because they're running a dehumidifier in their north room at this time.
And yes, they were growing a lot of crops that were heading outside at that point.
Cool. So they're also using it as, you know, a regular kind of starter greenhouse. And looking with a little more granularity, this is also from the Madelia site. This is looking at a series of 6 nights in January of 2019. And I pulled this out because this was the second polar vortex of last January. And so temperatures here, they're listed here. This was the low temperature for the day, or the night rather. You know, 16 below, 25 below, 27 below. And these spikes here, these are charts that indicate the total electrical consumption over time. You can see here's each night, switching over to January 28th, 29th, so forth. You can see these spikes are the backup electrical heater kicking on. Only at one point did it actually kick into the higher stage of heating. And even on that super, super cold night here, 75 cents for the entire day worth of backup heat in electricity, and electricity being one of the more expensive energy sources. So generally, we're happy with how it's going. Some lessons learned. Well, rely on your local builder expertise, right? The plans are pretty straightforward. They've been developed so that pretty much anybody with some decent construction familiarity should be able to assemble it. Material and labor prices vary very widely, and this was kind of one of the biggest surprises of building these 5 different greenhouses around the state. Construction prices for the entire greenhouse ranged from On the low end, 22,000 to the high end, 68,000, operating off the same set of construction documents. And so that reflected a couple things. One was how much labor they had to hire out, or that they could do themselves or volunteer build, and also material prices. The materials generally can be ordered from your local, big box builder supply store. But things like excavation, masonry, block work, foundation work, and actually the rocks for the rock bed varied quite drastically in price. The block work itself can be very expensive. These asterisk items here, these are things that we really tried to address with the farm scale winter greenhouse design, and I'll come back to that. Set up your sensors and loggers right away. This is one of the things, talking about looking at the performance, how is it actually working? I really encourage you all to monitor your greenhouses. Put in temperature sensors. There's a number of relatively inexpensive systems that tie in with either Bluetooth, so you can actually download the data off of it right to your phone, and then you can push it up to a kind of a portal where you can make sense of all that data. And if nothing else, just write it down in a notebook. Keep track of what the highs and lows were. What the light conditions were. Was it sunny? Was it overcast? All these sorts of things to help you try to identify patterns that can hopefully help you improve production over time. But set that stuff up right away. Ventilation is tricky. In particular, we specified some just typical crank out casement style vinyl windows with a double pane glass and insulated glazing unit in there. And the main reason that we went with that was because they seal up nice and tight, and we were really trying to be careful about air sealing. Again, we were trying to have full control over that enclosure, that volume of air that we've created, not have any drafts and so forth. Most of the greenhouse ventilation appliances out there, the typical metal louvers, they, first of all, they're metal, so they conduct heat very readily. And so they're freezing cold, literally. So they'll, any warm, moist air that hits that is going to condense out and freeze right away. So it's going to inhibit their operation. And generally, they don't seal up very tightly. So that's why we went with those windows. However, we were still running into similar types of problems where that warm, moist air, when it was trying to exit, would condense out and create problems when they were trying to seal it back up again. So still looking at other better ways to ventilate in super cold conditions. One thing to recognize is that when the sun is shining, it can easily be 90, 100 degrees in there if we don't have good ventilation, if we're not circulating the air through the rock bed and so forth. So we need to make sure that we have ventilation, but it can be tricky on those clear early February days when it is, 30 below outside. Oh, Carol's got a guest consultant. Shade cloth is something to consider. I know down in Madelia, they use shade cloth to help mitigate the amount of solar gain that's coming into the space and avoid overheating. Last thing just mentioning is that glazing is reflective, and here's a picture of the Bemidji greenhouse with the sun reflecting off the glazing there. So onto the farm scale winter greenhouse. I look at the V2.0 design as a very, it's a goal-oriented design, right? We had a set of parameters that we were trying to achieve that was minimizing our backup energy use, so prioritizing passive solar design and really optimizing for, November to March production window. So it has a very specific set of performance parameters that we're going for. So I liken it to something like the Formula E. This is the electric car version of the Formula One race. And so this is an all-electric car. Some other analogies, gets people excited. It's iconic. It's got a very specific form, recognizable as, a V2.0. It is high performance under a narrow range of conditions, right? So it's not designed to go year round necessarily. We are finding that it works better than anticipated, partially because of the steep glazing angle also helps reject heat when the sun gets higher in the sky. And the thermal mass actually winds up being a temperature stabilizer when it's overheating in there. So we're actually able to cool off the air that's inside and help maintain the temperatures in the growing area. It's highly responsive, but you do need to learn how to operate it correctly, right? We've created a very specific microclimate. It's not like growing in the field. It's not like growing in a hoop house. It's different and has its own set of parameters. It's not easily adaptable. Again, if you do make changes to this, it will affect portions of the performance, right? And that's not to say that it's not going to work, but you know, really, this has been a coalition or a coalescence of different design approaches to try and optimize all of it. And it was expensive, as we found out. And that wound up being one of the single biggest responses to our work on this, is like, how can we make this more accessible to people that are interested? And a lot of people were, you know, we're looking for a lower price point, lower capital expense to get going. So maybe everybody doesn't need a Formula E racer. Maybe they're more comfortable with something like a Prius wagon, something like the farm scale winter greenhouse. And so this is a rendering of what it looks like on the outside. Major features of this: one is increased size. The footprint of the 2.0 was 24 by 24. The footprint of the farm scale greenhouse is 20 by 60. So almost 3 times bigger. It's reduced cost, construction cost per square foot. The average construction cost per square foot for the 2.0 was about $75 a square foot. And for this one, it's about $25 a square foot. It uses a more robust wall for the insulated, the opaque walls on the east, west, north sides and the roof. So we're moving away from a cavity wall, moving away from the mineral wool, and moving to an entirely exterior insulated system. So from a building science perspective, this is a variation on what's called the perfect wall, where you've got all of your structure inside where it stays warm and it's controlled. Then you have all of your control layers. This is your weather resistant barrier, your vapor barrier, your air barrier, then your insulation, and then any cladding in a rain screen type of application on the outside. And I can dig into all that stuff more deeply if you want. We're also working with a pre-engineered glazing wall. So I look at this as kind of a hybrid assembly, where the south side of the structure is essentially a hoop house and all the rest of it is an insulated box, essentially. So a cross between maybe a cooler and a hoop house. I look at this as more of a modular type of structure than the 2.0, the farm scale. I see the top portion, the above grade portion, as more of a shell, and that can be moved around. You could put it over a thermal mass, you could put over just bare ground. And the type of thermal mass that you choose to use, whether it's rock bed or whether it's something more along the lines of a GAT system where you've got transit ducting moving through the soil, that, you know, that's going to vary. People's ability to employ those depends on a lot of things, including their budget, their site conditions, their water table, whether they've got a relative with an excavator, right? You name it. So we're trying to make this a little more flexible depending on your site and budget. You can also scale this slightly, you know, east to west. You can extrude it in the east to west direction. It's trickier to do that in the north-south direction because that starts affecting the light penetration back into the space. We're also looking at some other simplified ventilation prototyping. Here's what it looks like in elevations. Here's the south side, of course, all glazing wall. This is a double glazed polycarbonate rigid glazing, pardon me, over that typical hoop house style truss and unistrut system. The roof is 2x8 with 2x8 rafters with sheathing, and then continuous insulation over the outside of that. And of course, insulated east and west walls. People ask whether it's better to try and put glazing on the east and west sides. Really, from an energy standpoint, the amount of sun energy that you get in through glazing on the east and west sides is less than the amount of energy that you lose when the sun isn't shining. So ultimately, the east and west sides become an energy liability, right? They're a net negative on the east and west sides. And so I generally encourage people to insulate their east and west sides and really optimize their south side if they're trying for, you know, true winter production, right? Of course, if you want to extend the seasons, it may make more sense to try and have those either be partial or full glazing. The other little side note to that is that it's probably more recommended to put additional glazing on the east side because, again, that's where you have the early morning sun coming in. You want to try and heat up the greenhouse as much as possible after the long, cold night, right? So you want to try and get that temperature back up as quickly as possible. Here's a schematic for a really kind of a geo-air heat transfer system. So this is not the rock bed system, but what a thermal mass or thermal exchange system might look like in the farm scale winter greenhouse. There's 4 independent systems. Again, there's an intake duct. The air gets drawn down, the hot air gets drawn down into this distribution manifold. I guess this isn't really a plenum. It's a manifold, and then it goes through transit ducting, which is buried in the soil below the area that you'd be working if you were working directly in the soil. You could, you know, and the main reason that we're suggesting this is for cost and complexity, right? It's not convenient for everybody to dig out, you know, 2-4 feet of soil and then replace that all with rocks. That would be a pretty fairly expensive endeavor. So depending on, again, what your goals are and, you know, your budget and you know, availability to work with those more complex systems, you can make different decisions regarding that. Here's the plan. The ridge beam runs roughly along here. We've got columns that support it in the middle. There's that kind of packing shed storage area on either side. Again, these are acting like an airlock. So we've got entrance to the exterior here, and then the entrance that goes between that storage area and the growing area here. Total growing area for the farm scale is just under 1,100 square feet, with about 160 square feet for the storage area. Again, the east, west, and north walls are all insulated. So I want to point out that there's a number of different variations. Again, talking about the shell is kind of an independent setup, and what you do below grade, there's a number of different alternatives that you could undertake depending on you know, how deep you want to excavate, how extensive a foundation that you want to put in, et cetera, et cetera. So this particular variation shows a helical pile type of foundation. And these are also called ground screws. They're a big pipe that has a huge thread down at the bottom. And that thread acts like a big flange that helps act like a footing. So it absorbs the gravitational load of the greenhouse, but almost more importantly, it's helping reduce uplift. And so you see kind of miniature ones of these to help tie down like portable tents and so forth. It's basically the same principle, only larger, you know, for a building. These are often used to support decks and so forth. They go down and they, you know, are supposed to go down below the frost line, essentially. In this particular case, we've got those piles supporting a grade beam and the columns. And then around the outside of that, we've got 4 inches of XPS insulation. So this could be simply trenched in. So dig a trench with a ditch witch or something like that, slip the insulation down. And as long as you've got that barrier, you're preventing the heat from moving out of your controlled, you know, your heated area in here and out into the surrounding soil, right? The other thing to note about this, is that this insulation is continuous with the insulation that's above ground, right? Here we've got our 2x4 stud wall. We've got our sheeting. It's a zip sheeting. That means it's an OSB. It's a kind of a panel, you know, a big 4x8 panel. And then it already has the water barrier pre-adhered to the exterior side of that wood panel, okay? The seams get taped, and that becomes essentially our weather barrier. That's the waterproof barrier. On the outside of that, we put a drain wrap. So we get some drainage behind there, and then we put our insulation on the exterior. What this does is that it provides continuous insulation. We don't get any thermal bridging, and we make sure that we're protecting our wood from, you know, big variations in temperature, and also, of course, we're preventing any water from getting back there. Outside of the insulation is our cladding or our siding, right? And that could essentially be anything. It could be wood, it could be vinyl, it could be metal, it could be fiber cement, whatever you want to put out there. But importantly, you want to put it over some furring strips so that there is an airspace behind the cladding so that the wall can dry out if any vapor or moisture should get behind there, right? Note though, this is continuous all the way around that shell, all of the opaque parts of the greenhouse. That's all continuous insulation all the way around there. This perimeter insulation goes all the way around the outside and below grade. Okay, I think, quick question here, the farm scale version design will be available in about 2 weeks. I will, let's see, what time we got? 10 after 3. I will explain a quick variation, and then I'm going to go to the 3D model, which might help explain a couple more things. I think I will jump into some questions before I go to the 3D model, though, just to see if there's anything that needs to be addressed right away. Here's a variation of what could happen below grade, right? We still essentially have the same shell above grade, but at the footing, instead of using the helical piles, or you could conceivably use a block wall, just like we had on the 2.0, if you want to hire a mason or you want to do it yourself, you can put in a stem wall on a footing. Sure, work fine. In this case, we've got a grade beam. And so this is a 4x4 plastic lumber. You often see this used in like landscaping projects and retaining walls and that sort of thing. You could use treated lumber here if you wanted to. The reason I'm going away from treated lumber is that it doesn't actually not ever rot. It will rot just more slowly, but plastic is going to be there pretty much forever, right? So we don't have any danger of that rotting out over time. And if we had to move the greenhouse and reassemble it somewhere, we could still, potentially reuse those pieces. Yeah, and also if you're looking for organic certification or something like that, there's cautions against or prohibitions against using treated lumber in the growing area. So that essentially becomes the footing for the greenhouse. This is typically secured with larger ground screws, right, that would go down and hold that footing in. The other thing here is that we've got perimeter insulation, and then we've got the Swedish skirt, or what's called a shallow frost-protected footing type of insulation system. Instead of digging a trench down in the ground and burying the insulation vertically, we can also put the insulation out horizontally in kind of a skirt around the outside of the greenhouse. This helps prevent heat from migrating up and out of the greenhouse. It prevents frost from coming down here. We do have some conduction that would move through our heated area in here into the surrounding soil, but generally we're creating this kind of warmer heat bubble underneath the greenhouse with this, right? This could be thickened if you wanted to increase that thermal resistance. You could also combine the two if you wanted to put down vertical insulation and along with skirt insulation. But depending on your site, if it's wide open, you've got plenty of room, you may want to look at different variations for protecting the thermal mass or insulating the thermal mass. All right, I am going to just take a quick break and answer the questions. Answer some questions, and then we'll get to the 3D model, okay? So here's a good one. Since most heat is lost overnight, have you had anyone install a manual thermal wrap over the glazing at the end of the day? This also relates to another question up here I thought I saw about, I think it was in the registration questions. Does the structure utilize an energy curtain at night, or could one be retrofit? And so these are referring to a couple different strategies that we see in greenhouses. I'll answer the first one first. The energy curtain refers to, really, it's kind of a sheet of fabric that goes just over typically what, right over the plants in a typical greenhouse. What that does is it lowers the amount of volume in the entire greenhouse. It reduces the amount of basically the air circulation that's happening in the greenhouse, and helps to reduce transmission or conduction through the outside walls of the greenhouse. That can help, but it's really more of a strategy that's used in typical gutters connected style greenhouses, larger, much larger operations that are already hemorrhaging massive amounts of heat through their glazing wall structure. So the energy curtain really helps cut down on their margin, right? But in a structure that is already so well insulated, the energy curtain isn't going to do a whole lot to help us on the inside of the greenhouse, right? More effectively would be to put some kind of thermal blanket against the glazing wall, right? My preference would be to put it on the exterior, again, looking at continuous insulation around the outside so that we don't have any thermal bridging on the way through. We also avoid things like condensation and then subsequent freezing of any humid air that might come against that or get trapped between our thermal wall, our thermal blanket, and the glazing wall, right? There's a lot of different approaches to this. People have taken different approaches, come up with different styles. I know the greenhouse down in Madelia, actually, they use a shade cloth that also helps, basically insulate the interior of the glazing wall as well. This, though, I think this is kind of like the holy grail of deep winter greenhouse operation. To the question that was posed, yes, most heat is lost during the nighttime. So if we can figure out a way to beef up the insulation value of that glazing wall whenever the sun isn't shining, that's huge, right? I haven't really seen any climate suitable solutions yet. You're probably all familiar with the Chinese solar greenhouses that have been around for literally decades already. I mean, they are light years ahead of us looking at passive solar greenhouses. And they literally have square miles under, under passive solar greenhouse or growing in the greenhouse. They use it's kind of like a quilt, if you will, with basically tarp material on either side. It's a thin quilt that then gets rolled over the outside of the greenhouse. Prior to that, it was actually a woven straw mat that would get rolled down on the outside. Great strategy, but they have a much more temperate climate than most of us do that are looking at a deep winter greenhouse. So we need to address those situations of high wind, really extreme conditions of, freezing, sleet, all that other stuff. And so figuring out the right approach to something that can do an effective job of insulating and can deploy, right? It can be put on and taken off. Despite whatever conditions there are, there's pros and cons to having it on the outside and on the inside. Again, this is, the person that answers this question is going to be very well known, I guess. It'll be popular in the greenhouse world. Let's see. Is the back room being heated in addition to the greenhouse portion? No, generally we're relying on heat from the greenhouse to migrate in there. Some people will leave their door open. However, if you do that, the humidity will also move back in there. And since it's colder, a lot that humidity can drop out. So I have seen, I don't know if Pillager has a backup heater in their packing shed. I don't know, Greg, if you remember. But it's something to be mindful of. Do we have plans available for sensors and loggers? I've got a schematic drawn up for the thermocouples, but I don't think that would be something that would be, I wouldn't expect, anybody to set up their own similar kind of thermocouple system. That said, there are systems available from a couple companies. One is called Onset, O-N-S-E-T. They make a series of different types of monitors called Hobos, H-O-B-O. And those are the Bluetooth enabled ones that I referred to earlier. They do temperature, they do humidity, they do light intensity. So you could get a couple of those arrayed through your greenhouse, and then you could have a pretty decent idea of what's happening in there. They also have ones that have a longer sensor or a longer cable between the actual sensor and the sender, right? So you could drop it down into your thermal mass if you wanted to. There's another company called Monnit, M-O-N-N-I-T, that makes similar types of sensors. Both of those companies also have a web-based portal that you can send all that information up to and help, do graphs and different types of stuff like that, right? Let's see. Could you implement a sort of awning to reduce heat in warmer months? I would probably use some kind of shade cloth first. I actually really like the shade cloth deployment technique that they have in Bemidji, where they put some a structure on the outside of their glazing wall to help keep it away from the glazing wall so it doesn't get scratched, and actually provides a little shading for the glazing wall. So you're shading it before that heat actually gets into the greenhouse. Shading is much more effective on the outside of your window, in short, right? Awnings work better than blinds, for example, because the heat has already come through your thermal envelope. But an awning itself on the greenhouse could be an issue with wind. That would be the one thing that I would really watch out for, especially if it's any kind of like fin or something that's projecting past the glazing wall. If it's open to the air, it can act like a big sail essentially and get torn off pretty easily in high wind. Has this been built? No, the 3.0 design has not been constructed yet. We are in process of building a couple of these in partnership with a couple organizations in Minneapolis. Well, honestly, we were supposed to be doing construction right now. That's been slowed down a little bit because of COVID, but they should be completed within the next 2 months or so. So we should have a better sense of the construction process, and we won't have any performance data until, of course, next spring, though, of course. Any groups helping to design greenhouses? Well, besides this one, I would say plug for the Deep Winter Producers Association Facebook page. Yay! If you haven't already, check out, and you are on Facebook, or maybe this is one excuse to go on to Facebook, ignore all the other stuff, is the Deep Winter Producers Association. This is a group of enthusiasts and experts. All of Greg and Carol and I are on there quite frequently, just kind of troubleshooting and helping answer people's questions about greenhouse construction, design, performance, operation, all the above. So that would be a really good resource to tap into. How can we get your contact information? Well, you can email me at dhandeen@umn.edu. That's dhandeen@umn.edu. Have we considered Solex as a covering? Solex is it's a polyethylene material, a double-walled material, and they make it in a couple different thicknesses for varying R value. It would work. The one issue though is that it's not going to allow quite as much solar heat through into the space, right? The solar heat gain coefficient is lower than basically a clear glazing would be. Solex is very cost effective. I mean, their R value is rated pretty high to the point where I'm almost skeptical. So I know it's a cost-effective way, and it does a good job of diffusing the sunlight, which is actually what plants prefer over direct sunlight. But I don't know. I haven't used it yet. I just I'd be curious to see as a comparison how much heat it does allow to go through. Planning to ventilate. How are we planning to ventilate these structures, particularly in winter? So I will go back. I've got a ventilation prototype. I don't have it with me here to be able to show you, but briefly, these, here, these little circles here in the side of the elevation, they indicate an alternative type of ventilation strategy, basically multiple small ducts. There's a screen in the middle, but they're insulated on both ends. You could pop the insulation out and basically they would be manually operated at this point, but it would allow enough cold air infiltration into the space. I think that could be augmented with some kind of inline duct fan that you could then, of course, like basically put a cork in to seal it up, right? The big issue with our current greenhouse ventilation strategies is that, they're louvered systems. They're designed for moving massive amounts of air, and also they're not really concerned about being super tight, right? That as an aside, I have seen, very well insulated and nice, like double gasketed louver systems. But those are typically designed for high-end heating and cooling systems where you've got dampers that are controlling indoor air and so forth. They're pretty expensive and they require some kind of like separate automated operator or, a motor to operate them. So I'm looking at a way that, can simplify the operation, is less vulnerable to, frost or air leakage, and, still is pretty operator friendly, right? I should also just say that we get a lot of questions about automation and, could you automate this and could you, put some kind of controller on the ventilation system? And yes, you absolutely can, right? The way that we have our ventilation set up in the 2.0 systems, those vinyl windows, is using what's called it's a mega vent. They're built by a Dutch company, and they have essentially, you've probably seen these for cold frames and so forth. It's a paraffin charged or paraffin filled cylinder, and as it heats up, that paraffin expands and it extends this cartridge, right? Which basically then actuates or opens the ventilation, right? It opens the window. As soon as that cools off, it contracts and it shuts the window. So it's a nice, super low tech way. No electronics, no motors, no, exterior sensors. You just kind of dial this little cartridge, and it's super simple, right? My perspective on this is that the more complex of a set of systems you get together, the more places it can go wrong. So if you have a high degree of I don't know, how do I say, delicacy? If it's a very delicate system, if you're relying on this thing to talk to this thing in a very specific way, which then, moves this actuator that is the entire backup control for your entire system, there's a lot of vulnerability there. And so what I'm trying to do is simplify as much as possible the system so that we don't see failures like that, right? So, that's our approach to it. But it's always tricky. Yes, you can automate, absolutely. You can throw automation at it if you've got the patience and the budget and, you like troubleshooting, that sort of thing. The curved south wall seems to be expensive and reliant upon a manufacturer. Would it be cheaper and more accessible to make that south wall 2 flat surfaces? Yes, you absolutely could. The thing that I like about the curved wall is that it's still using one continuous piece of polycarbonate that gets laid down over the top. Of course, there's seams in between each one, but the thing that we're trying to avoid here is a seam between maybe a vertical wall and an angled wall on top of that, as we'd see in a lot of other winter greenhouses, right? Any place that we've got a joining, or we've got a joint or a seam or something like that, that's where we're going to get problems. That's where we're going to get separation of materials. Carol's gesturing because she's had some issues with this, and subsequent air leakage. It's since been repaired as far as I know, but there were pretty decent sized gaps in the glazing wall on Carol's greenhouse. Just as an example.
Yeah, you really helped fix that, though.
Yeah, thank you. All right. What else? Any research using a heat exchanger for temperature control? An ERV or a HRV could be a really good operation or a compatible technology for this. I don't know of anybody that's incorporated one of these. Basically, this is the type of appliance that would go into a house where you're exhausting stale air from inside the house, you're drawing in fresh air from outside the house, but in that process, it goes through a heat exchanger and it extracts the heat that would otherwise be exhausted out of the house. And so you get to retain usually about 80% of that heat and bring that into the incoming fresh air. I like that a lot. Except that it is, it's a relatively expensive piece of equipment, but, absolutely compatible technology. The other thing I like about that is that we're also then drawing in fresh air, which has carbon dioxide. And that's one thing that I think could use a little more research at this point, is that we've designed a very airtight structure which is great from an energy perspective, but of course our plants need carbon dioxide to really thrive, right? And so having fresh air come in also brings in carbon dioxide that the plants would then be able to keep using. Let's see. Where would you purchase the steel tubing for this greenhouse? Well, I mean, the company we're working with is Polytex. They're a greenhouse. They are a hoop house manufacturer out of southwestern or southeastern Minnesota. This is literally using half of their typical Gothic style 30-foot wide greenhouse assembly. It's the exact same thing. So we're working with them because they've got the production facility. If you know a fabricator in your local area that could emulate or do a similar type of bend steel tubing to this, work with them. Could the design be modified for the greenhouse to be built on a hill? And I'll answer this question more broadly because there were questions about this on Wednesday too, about berming it into a hill or burying it partially in a hill. I think it's a great approach to help basically get some exterior thermal mass, which helps moderate the temperature on the outside the greenhouse and provides more protection. Obviously, wind wash gets to be a pretty significant factor in this. So if you're out on the prairie and the wind is constantly blowing by there, it's it's drawing more heat away from the structure, and so it provides protection. The thing I will say is that you do want to insulate in between your greenhouse structure and your earth berm, whatever that is, because you're still going to get heat migrating through out of the greenhouse into that berm. And the other thing is that you want to make sure that you have drainage in there, because the one thing you don't want is for any moisture or rainwater or something like that. Maybe it's coming off the roof of the greenhouse and then dripping down, and then saturating in between the greenhouse wall and the earth berm, right? We want to make sure that that can get out in a way. Otherwise, you'll probably wind up with leakage problems through the bermed portion of your structure. So think of it as kind of like a basement. You're building a basement that's partially built into the side of a hill, right? You have insulation out there and you've got drainage out there on the outside of that, okay? Let's see.
It's a question about how deep the rock bed is. I think the 2.0 design.
In the 2.0, it's 4 feet deep. Yeah. That was basically in response to, well, we're going to be digging it 4 feet deep to put the footing in there. Since we've got it excavated, let's just fill it full of rock. What that winds up being is a huge battery, right? I liken it to, like any other electrically, or something that relies on energy storage. The bigger battery you have, the longer it's going to last, right? So that winds up being a really big battery. The two things that we're finding with that is that we could probably use more airflow through this big battery. But like I said, we don't have any concrete results yet about the sizing of the battery of the rock bed. Whether we can go shallower, or if it makes sense to use more or go deeper or something like that. But it is, it gets to be quite an endeavor, and not inexpensive depending on where you are.
With that more airflow, there's another question about using 2 fans, a push on one side and a pull on the other.
Yeah, good question. And yes, I think you could. That would help, belt and suspenders, your airflow. The reason that we have it on the draw side, though, is because we're going to have less variation in temperature on that side. That is the air that has already come through the rock bed. And so we'll generally see that somewhere in the range of 55 to 65 degrees, generally cooler. And the big thing is that the air up at the top of the greenhouse, that's going to be, 100, 105, 110 degrees sometimes. Really light and fluffy air, because the hotter it is, the less dense it is. It's really hard for a fan to move light, fluffy air. It's much easier for the fan to move more dense air, which is cooler air. So that's why we put it on the draw side. Still, that said, I don't think it would hurt to put one on the push side as well. Alternatively, I do know another, somebody who's building a greenhouse, not part of these, our research study necessarily, as part of the 5 greenhouses, but they actually put in 2 separate duct systems, or fan systems, right? There's still no transit ducting, it's still going through a rock bed, but they separated the greenhouse basically in the north-south axis, and then they have 2 systems, so 2 fans. They basically effectively doubled the amount of airflow that's going through there. I don't know, should we take a look at the 3D set of plans for the greenhouse? What do you think? Poll? I don't know how I do a poll now. I don't know if I can because I'm not the organizer. Let's see here. Okay.
People say yes. Let's see the model.
All right,
and then
let's check
come
it
back
out.
and finish the questions.
Okay. Close these. All right. Can everybody see this okay? All right. So this is the farm scale greenhouse in wireframe. And I can go through some of the features here. This is the plan. You've all seen this. The ductwork, essentially, how it would look inside the greenhouse, right? So you can see it laid out in here. From the front, from the rear. But probably more interesting to most people is going to be the section and what this looks like. So I can dig into a couple things here. Importantly is the structure. You'll notice here's the 2x4 stud wall that is, again, there's no interior finish here. This is open to the inside so that it can, dry out. It also is ambient temperature of whatever's in the greenhouse. So we don't have a temperature differential that that moisture would conceivably condense out onto, right? On this side, we've got the, got the glazing wall. There's a stud basically that gets screwed to the ridge beam up here that receives the top end of the truss, and there's another stud down here on top of the glazing wall, or on top of the sill, pardon me, that receives the bottom end of the truss. Then these horizontal pieces, they're referred to as unistrut systems. These act as purlins, stabilize the whole thing, and that's what the glazing wall actually gets attached to. Let's see. I think I can disassemble this a little bit here. Maybe better would be to go through some of the variations. I've got all of them turned on right now, so it's a little bit confusing, but this could be one variation, for example, right? And pardon me, it's doing a section cut through the outside line, so it looks like it's hollow, but you'll just have to imagine with me that here is your foundation wall. Let's see if it lets me do this. Oh. Here's your foundation wall, here's your concrete block right here, and then on the outside of that is the vertical insulation. Again, this would be something, if you're going for a more traditional build with a strip footing and a stem wall, depending on where you are. Oh, and this brings me to a couple questions that have been asked already about codes and how the authority having jurisdiction would look, or the AHJ would look at constructing these. So depending on where you are, you may have more or less enforcement of the codes. For example, in the city of Minneapolis, we were able to get a conditional use permit because we don't have a permanent foundation. We use that grade beam style foundation rather than a permanent footing and strip footing and stem wall type of approach here. But depending on where you are, you may need to go down deeper if you are putting in a permanent foundation. Alternatively, if you, let's see here. Somewhere I have, sorry, something is pokey here. Come on. Well, maybe this isn't going to work. That one? There. Okay. So alternatively, you could use the helical pile foundation instead. Again, these are arrayed to support the grade beam. You could put them underneath the columns if you wanted. In this case, there is a big footing, concrete footing under each of these. But these go in, essentially there's it's like a bobcat with a fancy attachment on the top that just literally screws these down into the ground to the right depth. And so, you know, you do have to hire that out, but it's a pretty convenient alternative to getting, I know, excavation and then concrete footing and block wall or something like that. And then alternatively, instead of going vertically with the insulation, we could go with something like that skirt insulation. Again, this is laid under the ground around the perimeter, right? So you basically just have about a 4-inch deep layer of soil on top of this surrounding skirt insulation, right? So we can ooh, my computer is acting pokey. All right, enough of that. I will try and hit some more questions. It's 3:42. All right, where are we? Where to get plans for the 2.0 or 3.0? There's a link in the Q&A to the Deep Winter Greenhouse RSDP website. That is where all of this lies. The 3.0 plans, or sorry, we're referring to it as the farm scale greenhouse, okay, winter greenhouse. That said, that's primarily because we're looking at being able to extend the production season for a while. It's not gonna, you know, have the same type of heat retention capability as the 2.0. Obviously, we don't have as much insulation. We've got more glazing wall, which again is gonna lose more heat. And depending on what type of thermal mass system you use, we'll have a difference in how much heat we're able to store. But all of that stuff, all of our reports, all of our research is available on the Deep Winter Greenhouse U of M site. We haven't found a manufacturer for the entire kit. I don't know anybody that's doing that besides Ceres. Again, that's CERES. They're a consulting and design company based out of Boulder, Colorado. I know those folks and they do really good work. I have a ton of respect for Mark and his team there. But I know, well, I've heard that they're kind of spendy. So depending on what your budget is like, you know, that might be one route to check out. There was a question earlier about looking at energy usage of comparing the farm scale winter greenhouse to just a regular hoop house or gable style connected greenhouse. My initial energy modeling calculations compared just the above grade structure, okay? So not including any effects of a thermal mass, SHCS, GAT system, or any of that kind of stuff. But above ground only, the insulated version, you know, this farm scale greenhouse style, saves about 40% of the energy that would otherwise just be lost in a typical hoop house, right? How will the V2.0 perform if we have hydroponic bed in our greenhouse? Oh, hydroponic bed in our greenhouse. Well, this question was asked on Wednesday too. I don't think it will. It won't affect the thermal performance much. I would recommend trying to control the temperature of your water as much as possible. I would try to prevent as much excess evaporation as possible if you can. We expect that there is going to be some condensation down in the rock bed, right? And most of that is just going to trickle right down and out of the rock bed. One important note about the V2.0 is that there isn't any insulation on the bottom underneath, separating the soil below from the rock bed above. You could do that if you wanted to, but in my estimation, the difference in temperature between the rocks at the bottom of the rock bed and the soil below them is not big enough to justify putting insulation in there. Insulation works best when there's a big difference between the temperature on one side versus the other. And if it's pretty close, it's not really worth it. We just thought it was excess, expense and hassle. But that's all to say that the bottom of it is able to drain. That brings me to another question I saw up here recently, which was about what do you do if you have a high water table? That's a very important consideration. One thing you do not want is water actively flowing through your thermal mass, because that is literally going to take the heat that you've worked so hard to store into this rock bed. It's literally going to take it right up, right? That cool water is going to take it away. So what we've seen is a couple different things. One is elevating the entire structure, right? And so they essentially bermed up around the bottom of the foundation wall slightly and elevated the entire structure off of what it might be otherwise. The other thing that we saw, the location in Pillager, was that they essentially built like a basement. They put in perimeter drain tile, and they've got a sump basket, and they've got a sump pump back in, up in the north room, and that turns on every once in a while and kicks the water out that that might gather and down within the foundation. So a couple different ways to address that. What else? Is pebble size important? Can you vary the size depending on availability? Good question. This is what I'll say. If the particle size is too small, as the air moves through it, it's going to heat up really quickly. And then as the air moves through to extract the heat, it's going to cool off really quickly, right? So you're going to have pretty high response rate, but it's not going to store it quite as long. If the particle size is too big, if you've got a big rock, it's going to take a really long time for heat to migrate in there and charge up, and just as much for that heat to be able to get back out. I like the 2-inch particle size because it does a decent job of allowing heat to penetrate and for it to go back out. It's a decently sized particle for the type of time scale that we're looking at, which is generally a couple days to maybe a week, depending, right? We're not, and I should be clear about how long we're looking to store heat with this rock bed. We're not looking at banking a whole bunch of solar heat during the summertime to extract from it all winter long, for example, right? That would be a huge heat battery, and the way that we would charge that up and extract it would be different, right? What we're looking at is much more stabilization on a daily basis, or maybe a couple, 2-3 days, right? Looking at it at lasting us through a couple cloudy days during the middle of the wintertime, for example. So that's the important thing here, right? people ask about different types of thermal mass. Could you put it in a sand bed? Could you use a hydronic system? Could you use water to carry the heat? Yes, you can. Do it if it makes sense for you. Again, the reason why we went with air as the medium to transfer heat in this is because air is cheap, it's simple to move, and it's not a big deal if it spills, right? All the other stuff, you've got pumps, you've got some kind of antifreeze solution in there, so you avoid freezing. There's just, again, more things to go wrong. Rock and air is pretty simple. There's a question, do you have any experience using phase change materials such as thermal tile? Phase change materials, I think, are a very compatible technology. For anybody that's not familiar, these refer to something like, wax is a good analogy, where you add heat to wax and it changes from a solid to a liquid. And then when it changes from a liquid back into a solid, it gives heat back. And so there's a number of different products out there that have basically encapsulated some type of phase change material that absorbs the heat. It stores that heat in a phase change and then can gradually solidify again and give that heat back into the space. And so the one that we see most often is called BioPCM, and there's a company called Suncatcher Greenhouses. I think they're based out of North Carolina. They've got a design called the Carolina Mountain. You can check out their website, and they've got a number of good photos in there of, it's essentially like a big blister pack, and each of these blisters is filled with this phase change material, and it covers the entire inside face of their solar greenhouse. And that's exactly what that's meant to do. It's acting as a stand-in for a thermal mass. It's still storing heat, but instead of storing it in mass, we're storing it in a phase change. And so, again, I think it's a totally compatible technology, totally compatible material. There may be some additional expense associated. You also want to be sure that the temperature at which it changes from a liquid to a solid corresponds to what you need in your greenhouse, right? If you use just like a regular wax or something, that's not going to change into a solid or into a liquid until it's 100 degrees. At that point, that's outside of when you actually need the utility of that phase change. So you can't just use any material for a phase change material. You want something that's tailored to your production zone, your desired production temperature. Do the plans on the U of M site discuss the sizing of ductwork and fans? What we do is specify what we have, the ducting to be able to move stuff through for this size greenhouse. As I mentioned before, I would probably try and increase the amount of airflow through the rock bed if possible. So there isn't a whole lot of discussion around there. The rule of thumb is 5 air changes per hour through your ductwork system. I don't know if it's still available, but John Cruikshank, who originated the solar heating and cooling system, subterranean heating and cooling system, developed an online calculator. So I don't know if you can find it out there, but that can help you figure out how much airflow you have through your ductwork system. Right now, our plans or our set of materials for the ductwork and the fan is about 8.3 ACH air changes per hour. So we're above that 5, which is good. But again, like I said, I think we're still looking at trying to increase that. What element of the entire design, if done incorrectly, can really ruin the whole project? Put positively, what do you really want to get right? I'm quite concerned about budget. That's a great question. What is the single most important thing? I don't really want to duck the question at all, but I think the single most important thing for a winter greenhouse is making sure that it's airtight, that you have good control over the air that's in there, right? If you have any drafts, it doesn't matter how much insulation you have, it doesn't matter what R value your glazing is, it's just going to be, you're going to be losing that valuable heat in the fastest way possible, right? So really paying attention to your construction details. I'd say that is my single biggest word of advice. Any risk of venting greenhouse air with another structure, sharing heat oxygen between greenhouse and a home? or a barn, I would say it's very appropriate to add to an outdoor structure. I know Carol's they built theirs onto their garage. There's one in northern Minnesota that's added onto the side of a barn. So I think those types of structures are appropriate. I would caution against attaching it to a house, only because if it's not carefully designed and all the materials are where they are supposed to be from a building science perspective, you could actually wind up with too much moisture in your house. You could wind up rotting the walls in your house, and especially the wall that is shared between the greenhouse and the house. So I really encourage you to talk to somebody who understands building science principles and ventilation and moisture migration and all of those inherent issues in a growing space before you go ahead and attach it to a greenhouse. So I generally will dissuade people from doing that. I've been in places where, you know, it's a wonderful experience and it's integrated well, but you just have to be careful. You know, you don't want any unintended consequences down the line with, you know, mold and mildew and rot. So yeah, just be extra careful. What types of rocks better than others? Not size, but the type of mineral. Well, that's a good question. Generally, you want something that is, you know, more along the granite, or, you know, it's you know, it's solid. It's not porous. Limestone doesn't really work very well. Pumice, for example, right? There's just so much surface area that, you know, it really is going to go in and out quickly. So I really like river rock. Smooth surface, I prefer to a jagged surface, mainly because that allows the air to move through more easily. There's literally less friction as the air is moving through the space. That said, of course, it does help churn things up if you have jagged surfaces. So we have seen, we have different types of rock in each one of our greenhouses, actually. Some is river rock and some is crushed granite. So hopefully when we get some more of these results, we might be able to draw some conclusions about what the differences in particle or rock type might have on the heat flow. Let's see, anything else? We done flow testing or power draw testing to determine where on the fan curve the fans are operating. Not yet. We do have airflow sensors installed, and so that's part of the data set that we're looking at with the with all the thermocouple data. So that should all come back to us at the same time. How does the steel tubing tie into the header? There is a plate with a round stud that's welded to the plate. The plate gets screwed in with lag bolts into the ridge beam, and then the truss basically slips like a sleeve over the tube that's coming out of the stud. We have a long, narrow lot. Could the design be modified to dig a long, narrow trench, maybe 8 feet wide, use native soil as the thermal mass instead of rock? Yes, if you want to use a, you know, like a GATSIS type system, I'd say you could bury that and use that. I think the question here that Joy is asking, Joy Happy, is about doing some type of external geo exchange system. And you're probably, if you've been doing your research on winter greenhouses, you've run across the citrus in the snow guy. That's Russ Finch down in Nebraska. And he basically has a partially sunken greenhouse. I think it's 4 feet below grade. And then he used a very similar type of structure to this. He built up on the north side, and then he's got a hoop house, almost a hoop house type structure that comes from the south side. And the difference is that he has run his tubes out in a big loop field, out and around, because he had the right type of soil conditions and he had plenty of space to be able to trench this stuff in. And so he ran this long, essentially a geo-air system out and then back to his greenhouse. And he uses that as a geothermal heating and cooling system. And that works great. If you have the space, if you have, you know, if you have the soil type, where he is, it happens to be in, I think it's in a river valley, so nice sandy soil, drains nicely. So that I think that's what she's referring to, and that works well, I'm kind of like thermal mass agnostic at this point. There's lots of ways that you can approach it. You might need a larger loop field to, to match the performance of the rock bed. The other thing is that the rock bed is really using the sun's heat to heat the rock bed, and the geothermal loop is really using the Earth's stable heat temperature to kind of condition the whole airspace inside the greenhouse. So you'd be looking at a more constant temperature probably inside the citrus in the snow type greenhouse that's coming out of that geothermal loop. But that's probably going to be more like 52 degrees, something like that, whatever your constant ground temperature is at your location.
Hey, Dan.
Would running the rock battery in reverse help cool if trying to use the structure year round? We don't run it in reverse. We actually are just keeping it cycling the same way. And that seemed to work just fine because you're still taking the hottest air, you're drawing it down, you're essentially putting the heat into the rock, taking it out of the air, and that cooler air comes up into the growing area. To reverse the airflow, yeah, I think it still makes more sense to just keeping it going in the same direction. I think reversing the airflow would then also mean that you should ideally change the location of your intake and your exhaust ducts, and turning, I don't know, the fan around somehow might be problematic, especially if you're using a centrifugal fan or something like that.
Hey, Dan, I'm going to interrupt you here. Let's let you know it's 4 o'clock.
Yep.
I guess I'll leave it up to you to see if you want to try to get all these questions answered, or maybe we can do it by email or some other way. There's
I'm looking through, it seems like we've answered most of the stuff that's on the Q&A. I think we should just call it. It's been a good 2-hour session, and like I said, you can feel free to email me. I'll try and respond as best I can. I want to be careful though. I do have another job. So, if you're looking for actual consulting work, there are consultants out there to help you, really nail, and dial in the design of your particular greenhouse. Yeah, but feel free to reach out, and yeah, thanks everybody for joining us. I think we got this one recorded, so this one will be up on the web. Again, check out the Facebook group. That's another great place to try and get some more advice as you're moving ahead. And yeah, that's all I got. Greg, back to you.
Share my screen, and put the last slide up here just so everybody has our contact information and knows what's going on here. Here we are. Thank you very much. The website, the quick link again, is z.umn.edu/DWG2020. And if you have your pen and paper handy, here are our email addresses. If you contact any of us, we will do our best to get back to you and get you an answer. That Facebook group, I'll also mention again, that Dan mentioned several times, is a great place to really tap into the hive mind around all things deep winter greenhouse, passive solar greenhouse. There are people in there from all over the upper Midwest and Canada and beyond who are experimenting with this type of stuff. And it's the type of people that just love to give answers. So if you have any questions, it's a great place to go get a number of answers from a lot of people with different perspectives. So with that, say thank you very much for joining our webinar, and check these out online if you want to look at them again. They should be up in about a week or so. And that is all. Thanks.